Okay, can you hear me? So first of all, thank you very much to the organizer for having me here today to present this overview on gravitational wave backgrounds with LISA. One thing I learned many years ago from my PhD advisor is that when you're at big conferences, either you give people good reason to listen to you or they will sleep. So I try with this slide to give 3 reasons why stochastic backgrounds are interesting for the whole audience. So first reason, these guys can actually be loud. This is something, and they can impact a lot individual sources measurement. This is something we checked in this paper with these people. What we did is to take signals, we saturate the most stringent bound we currently have in the LISA band, and the signals you get are something like these or these or these, for example. And what we checked is what happens if you then compute, whatever you want to do, inference on the individual sources for the different kind of sources you have in LISA. In this plot, for example, you can see what happens for verification binaries. Blue stars are the SNRs you get without including these loud cosmological backgrounds. Colorful stars are the SNRs you get when these backgrounds are taken into account too. And the takeaway message is if really we have something like this in the universe, which in principle is possible, forget about verification binaries. So they can be quite impactful. Second reason, something less dramatic. Let's assume we measure something coming from astro. What we can do is to learn a lot about astrophysical populations. I'm going to discuss this later on, but the main message from this is these 2 plots are showing constraints on population parameters, in particular stellar origin binary black holes, constraints from LVK measurements. On the background, you see the constraints from LVK measurements. This colorful thing on top is what you will learn when you combine those with measurements from LISA. So you can actually constrain things much better if you combine. Third thing, which to me is the most interesting. If we do measure something coming from Cosmo, we learn things about the energy physics, and hopefully someone in this room gets a Nobel Prize. Okay, after the end of the advertisement, this is the outline of my talk. I will start by telling you a few general things about stochastic backgrounds. Then I will tell you about astrophysical sources and what you can learn about astro from those. Then I will move on to cosmological sources. If I have time, I will say a few things about machine learning applied to stochastic backgrounds, and then I will move to conclusions. First of all, what are stochastic backgrounds? You can think of these as signals coming to us from the whole sky, more or less like the CMB. These guys have no phase coherency, so you cannot really try to find some coherent pattern. You just have to find power in this noise-like thing. This can be either of cosmological or astrophysical origin. Cosmological backgrounds come from violent processes in the early universe. Astrophysical backgrounds are due to the incoherent superposition of many weak sources. In either case, we can learn a lot out of these, and that's why they are targets for future detectors, including LISA. Actually, for LISA, 2 components at least are guaranteed, which are the stochastic background from stellar origin black holes and the one from compact binaries in our galaxy. In principle, you can have in the next years news from LVK detectors, or at least we already start to have some evidence coming from PTA, as was mentioned in the previous talk. So it's quite an exciting field, I think. Finally, if we really get to measure something, then comes the fun part of the game, which is trying to understand what the mechanism responsible for the generation is. And for that, you can try to look at the different properties signals might have. And out of that, you can try to, you can think of these as fingerprints for the different mechanisms, and checking, what are the properties. You can try to pinpoint what the mechanism responsible for the generation is. Let me say just a few words about data analysis again in general. So typically, what you assume for your data is to have a superposition of signal and noise. Yeah. Noise normally is just something stochastic with 0 mean and some variance. For individual sources, the signal has some coherent shape, some morphology clear, which you can recognize and pinpoint out of the data stream. For stochastic backgrounds, on the other hand, the signal has the same properties as noise. So what you should do when you try to get information on stochastic backgrounds is to look at the variance of your data, where hopefully signal and noise are uncorrelated. So you have the variance of the signal and the variance of the noise. Variance of the noise is the noise power spectrum. As for the signal, on the other hand, you basically have the real signal here, which is modulated by the response function of your detector. That's basically where you have to start digging if you want to get information about stochastic backgrounds. One more thing here, since I come from a theory background and I like doing cosmology, typically what we do is to convert PSDs onto omega units, because that's what we do for cosmology. So when you see omega gravitational waves or omega noise, keep in mind that this is just the signal or noise power spectrum rescaled by an f cubed and divided by the critical energy density. That's all. So when you see omega is still basically strain. This plot is taken from the Red Book, and it summarizes a little bit some of the signals we might have in LISA, both from Astro and from Cosmo. I will try to navigate you a little bit through this plot in the next few slides. I will start by talking about astrophysical backgrounds. First of all, you might want to understand how to compute the background coming from these astro populations. So there are two main options, well, more in principle, but let me just sketch two possibilities. The first way to estimate what the signal is due to an astrophysical population is just by taking the power emitted by a single source and integrate it over the full population, which is specified by some population hyperparameters here, and then the thetas here are the parameters of each source. So you integrate it over the full population, and then you know what the energy is. This is quite easy to do, and it was set up in this quite nice paper a long time ago. What you can do, which is a little bit more realistic and more accurate, is to, for example, use some iterative procedure, which is something we came up with in this paper 3 years ago now. So what you can do is to take catalogs of sources, compute the waveforms for all the events in the catalog, sum them all up together with noise. That's this gray band here. Then what you can do is to smooth it out and check what are the SNRs for the sources in the catalog when you also include the confusion noise due to all the other sources. You do this, you find out a set of sources which are sufficiently loud to be removed. You remove them, you get this cyan line. You repeat. At some point, you reach the point where this procedure converges. There are no sources which are removed anymore. And that is basically the estimate of your overall confusion noise due to a catalog. This thing you can do for all the different populations you can have in LISA. So here you see galactic binaries. This is stellar origin binary black holes. These are extragalactic white dwarfs, and these are MRIs. So in principle, all the different sources we have discussed in this symposium can lead to a stochastic background in LISA. In the next couple of slides, I'll try to say a few words about this particular case, so stellar origin binary black hole, which is something we have worked on in this paper with some collaborators. As I said, basically you need a catalog to start with. So you need to specify for all the sources, first of all, how many sources we have, and for all the sources, what are the properties. Luckily, for stellar origin binary black holes, we can take the populations given to us by LVK measurements. One important thing to mention, though, is that LVK measurements only tell us things up to some value in redshift. So when you want to compute the stochastic background, since it's sensitive to the whole universe, you need to continuate these populations up to very high redshifts. So the first possibility is to just assume that your stellar origin black holes follow the star formation rate. That is probably something kind of reasonable you can do. If you want to be a bit more accurate, you can try to include some time delay between the formation and the merger. If you try to do this procedure, what you get is basically what is shown in this plot. So the blue band here is what LVK measurements tell us. If you try to continuate this just using the star formation rate, you get this orange band here. And if you try to include some time delays, some models for time delays, you can get these black bands here. In the paper, we show how much the amplitude of stochastic background changes in LISA if you try to use any of these different models. In the next couple of slides, I will just stick to the orange case as an example to see what is the science we can do with these kind of signals. So in this plot, I'm showing you what happens since in here, in this plot, we are comparing the prediction we get from the analytical method, which is this orange line in the middle, with the iterative procedure. So the two things match quite well. So in this plot, I'm just showing you what happens if I use the analytical procedure to estimate the stochastic background. So you get this band here. And this band, the width of this band is set by the uncertainty on the population parameters given current LIGO constraints. So what we can do now is to check, given this possibility, how well we would constrain these signals with LISA. So what this plot shows, so the blue curve in the background is basically this band. So what I can do now is to take different injections, because we don't know in reality what the real signal is. So let's assume the real signal is the 5 percentile, 25, 50, and so on. These colorful bands tell you how well LISA will constrain that signal. So you can see that basically with LISA, we can shrink the accuracy by up to 1 order of magnitude. So pretty significant. This is quite nice. Then I can now explain a little bit better the plots I showed at the beginning. Let's assume we do a measurement of these signals with LISA. what can we learn about the population parameters? First of all, here for this plot, and for the one I'm showing in a second, I'm assuming now the injection to be the median value, the 50 percentile. What I can do is to generate, to combine the measurement I get from current LIGO detections, LVK detection, sorry. I can combine that with the information I get from the measurement done with Lisa. And basically what you see is that I would go from these, blue and things on the background to this orange and red cloud in front. So in this particular case, when I try to combine the measurement from LVK and from Lisa to infer properties of the mass function, I do improve a little bit, but not much. The case where I improve a lot when I combine Lisa and LVK is if I try to put constraints on the redshift distribution of these sources. And the reason is LVK only measures things at low redshift. Lisa, on the other hand, looking at the stochastic background, will measure something which is integrated over the full universe. So if you are pretty sensitive to what happens at high redshift 2, in particular, you are pretty sensitive to what happens around the peak of the star formation rate, let's say. So this part will contribute quite a lot. And depending on what is the steepness and how up I go here, it would change quite a lot the amplitude of the stochastic background. So that's why this constraint is pretty tight here. So main takeaway for astro signals, we can learn a lot if we measure this with Lisa. And we can improve quite significantly compared to what we get currently from Earth-based detectors. Let me show you this plot again. Let's now transit from Astro to Cosmo. For Cosmo, there are many possibilities. I'm not going to discuss all of them in detail. For example, I'm not discussing what here is with an abuse of notation called PBH. In reality, this is scalar-induced gravitational waves, but OK. What I will try to explain briefly in the next couple of slides is what are the ideas behind these lines you see in here. So let me start with inflation. Inflation is something we need to solve the early universe behavior of our universe. In the simplest realization of inflation, what you need is what you want is h to be constant. Sorry, to be constant because you want a to grow exponentially. You can see from these equations that for h to be constant, you need this guy to be 0. So you want basically a configuration like this one, where your field is in an early flat region of its potential, slowly rolling, and then at some point accelerates. So this is basically slow roll inflation. The interesting point is that if we just take the minimal realization of inflation, which is what seems to be compatible with CMB measurements at large scales, minimal realization of inflation won't source strong gravitational waves in the Lisa band. But if you go beyond the minimal realization of inflation, like adding extra fields or some other quite well-motivated things, you can pump a lot of energy into gravitational waves, and then you can get to have a signal which is detectable and loud. The very important thing is that the scale which you probe with Lisa is totally different from the one you probe with CMB. So adding this extra ingredient at scales which are quite far away from the ones from the CMB is totally fine in principle. And you can get information on scales which are at the moment unprobed. This, I think, is an important takeaway message here. Second mechanism, cosmic strings, which is basically this orange flat line here. So cosmic strings are topological defects which can form in the early universe if you have a spontaneous symmetry breaking. What you need is basically a configuration like this one, where you have this top hat Mexican potential. If you create a loop around this minima here, this is field space, this is physical space. If you have this configuration in field space, what happens in the physical space is that you create a loop here, which you cannot shrink to the identity because there is something which is impeding you from shrinking this. Basically, you would need this to jump on top of the potential. And that you interpret as having a string which pierces your loop. These things are generated initially, are stable. So they're going to be around and affect what happens in your cosmological evolution. Through evolution, they chop down into loops and emit a lot of energy. And in these models, typically, for this kind of objects, typically the spectrum is kind of nearly flat in Lisa, or otherwise you can end up having some kind of small bump here. So these models, anyway, are controlled just by one parameter, this Gn mu, sorry, which is basically related to the energy scale at which the phase transition is occurring. So if this is larger, you have more energy, and this bump moves to the left. If it's lower scales, it goes down. One last mechanism I want to mention, first-order phase transitions. So these two cartoons basically show you what is the difference between a first and second-order phase transition. So let's say you have a potential, which is changing with the temperature. Temperature goes down, the potential changes. In this case here, you just have your field, which is slowly rolling down from one initial minimum to another minimum. This is a second-order phase transition. In a first-order phase transition, what happens is that you move from the initial minimum to the new minimum, but during the process, the fields get stuck in a false vacuum, basically. So it's trapped here and cannot go down except through tunneling. What happens in physical space is that you have a sea of false vacuum, where bubbles of true vacuum nucleate, grow, collide, and emit a lot of gravitational waves. When this happens, basically, you end up having a signal which has this shape here, this green curve. And the interesting thing is that the position of the peak is telling you about the temperature at which the phase transition is occurring, first of all. Second important point, the phase transitions we expect in the standard model are all second order. So if we measure these kind of signals, this is telling us that there is something beyond standard model. So if we measure this, it's quite interesting, I'd say. OK, let me say a few words about what we can do with these signals. So at the moment, we have no data, but at least we can start doing forecasts and check how well we would be able to constrain the parameter space for the different injections. This is something we did in a series of papers, for example, from the Lisa Cosmology Working Group. What we did is, first of all, we chose templates. We checked with just Fisher formalism how well you can measure the templates parameters for different injections. Then we used an MCMC or nested sampler, whatever, to test that the results we get with Fisher are sensible with the ones you get with more accurate techniques. And finally, once you have constraints onto template parameters, you can map those back onto constraints on physical parameters and check what you can learn about fundamental physics given some signal. Let me navigate through you through an example. So let's take a power law signal, something very simple, just controlled by two parameters, an amplitude and a tilt. So these two plots show how well you would constrain the two template parameters for different injections. Blue means bad, red means good. So depending on the injection, if the signal is loud and quite tilted, you can measure these things pretty well, no surprise. These two crosses correspond to these two guys, where we checked that indeed Fisher results match with results obtained with with some nested sampler. And for this, we use this pipeline, which is internal to the Cosmology Working Group. But if you're interested in using this, email me and I can give you access to the code. And indeed, here we find that Fisher is compatible with what we get with MCMC. Fine. Then the interesting bit is, let me try to convert this back onto constraints on the physical parameters. In this left plot, so this again sticking onto a power law template. A power law is something you can get in many different inflationary setups. For example, here, these two plots correspond to axion inflation and to some massive gravity scenario. In axion inflation, the two parameters can be mapped back onto this epsilon and psi. Epsilon basically controls the steepness of the inflationary potential at the scale you're probing. And this psi parameter is basically telling you what is the coupling between the inflaton and some other fields, which are going to be around during the process. Interestingly, in this other model, on the other hand, since this is a model of massive gravity, and when you're in a curved space-time, there is the Iguchi bound, which tells you that there is a limit on the mass the graviton can have. This specific injection is actually ruled out. So, this is interesting to show that when you go from template parameters back onto physical parameters, you must be careful on what the physical informed priors are. So, for example, just using templates and that's it is not enough if you want to learn things about physics. So these results are for power law, but in principle, you can run the pipeline for different templates. That's what we did, for example, we did 3 papers, one on phase transitions, one on cosmic strings, and one on inflation, and we checked what we can learn for the different possibilities. These plots come from the phase transition paper. So in this case, the specific model we consider is a model where you start with a standard model Lagrangian. Thank you. You start with a standard model Lagrangian. You add a singlet, which is coupled to the standard model Higgs. And basically, what you can constrain when you map template parameters back onto physical parameters are the mass of the singlet, its self-coupling here, and the coupling with the standard model Higgs. So basically, if you manage to see the signals, you can learn a lot also about particle physics, which I think is interesting. OK, in the next couple of slides, I will try to say something about some new idea I'm working on recently, which I think is quite interesting and pretty promising. So traditional methods work well, but what about the other possibilities, and in particular machine learning? Here I'm going to focus on one specific possibility, which is what is called neural ratio estimation. So if you look at the posterior is likelihood times prior divided by evidence. Likelihood divided by evidence is what this little r is, which is called the ratio. So this ratio, if you do some algebra, what you can learn is this ratio is the ratio between joint and marginal probability. So what you can do is to basically train a network to, when you show data and parameters, you can build a classifier to tell you whether the two things are coming together or not. So the interesting thing of all this procedure is that it's likelihood-free, basically. So you just need a simulator. You have to show many examples of your data given model to your network, and the network will be able to tell you whether these two things are coming together or not. What we did is to check, OK, nice. So the first thing we asked ourselves is, does this work? So what we checked is what happens if we take some just very simple power law signal again, and we have this signal plus noise. This is what we get. So the black curves are the contours you get out of standard techniques. Blue contours are the ones you get with this machine learning approach. The two things match. We're happy. Actually, the code for this is publicly available at this repo. But we're trying to go a bit beyond that. Sorry, air conditioning got my voice. So what we try to do is to go a bit beyond this and try to see what happens if you include more complexity in the system. So more or less what we will really have in Lisa. It's not like we can hope for having clean data. So what happens if simultaneously having the data noise, stochastic background, and some sources I've not managed to subtract perfectly? Does this technique still work? And this is the result. So the black curves are the curves I've shown you before, so where there are no transients. Orange curves are the curves where I include the transients in the game. So in this plot, you see both machine learning, this Sakara method, against MCMC. It is not a totally fair comparison for the MCMC because I'm not including the possibility for removing the sources, but it's just to give you a feeling of how you would get a bias if you don't really manage to subtract all the sources correctly. On the other hand, for the machine learning approach, my contours get bigger, clearly, because there is some extra noise present in the data. I mean, that I cannot really resolve, but I'm not biased. So this is a quite interesting thing. And I've not really modified much the structure of the networks. It's the same network. I've just added some extra nuisance. That's it. So this is pretty promising to me. One last thing. We are actually working on a second paper. I was hoping to have this out by today. Unfortunately, it's not yet, but it's coming out soon. What we wanted to check is if this technique can be used to include also noise non-stationarity in the game. The technique the procedure we used for this is, again, a simplified setup, but it's still enough. So let's assume that this noise stationarity is on some scales which are short compared to the full Lisa duration, for the full mission, but sufficiently long that I can cut into segments where the values of the noise parameters are constant. So let's assume I can do this. I cut my full Lisa duration into segments. Segment by segment, I analyze, and then I combine. What we learn, first of all, which is totally non-trivial and pretty interesting again, is that if you take the constraints where the noise parameters are constant, is this orange line, and in black you see many realizations. Yes, I will conclude. And in black you see many realizations where now I'm drawing randomly these noise parameters segment by segment. And it's interesting that you actually do better. And the reason is noise is not, the errors are combined with inverse variance weighting. So the segments where noise is lower weight more than segments where noise is larger. So even if it's counterintuitive that you include more parameters, you still do much better. And this is nice, I think. And again, this code is publicly available, and the code we use for the response is also available on my Git. Conclusion, there's a lot we can learn out of stochastic backgrounds with Lisa, both for Astro and for BSM. What I think we should be doing in the next few years, in particular theories, is to understand a bit what are smoking gun observables? I mean, we need to pinpoint things which, okay, we see this stuff, then it means it's this particular signal and not this other signal, because this is not capable of generating this. So trying to understand really what are the expectations. I think we need also to improve on data analysis to try to use all the information that will be in the data, and also cross-correlating with other probes is a possibility, and we should think about that. Before concluding, at the moment there is an ongoing effort with other people, most of them sitting in the room, trying to compare the different pipelines we have for stochastic background analysis. Here is a list of people. I hope I've not forgot anyone. We're trying to check basically given data generated with Lisa node. We're trying to check if the different pipelines do give results which are compatible with one another and unbiased, and it seems like we're doing reasonably well. But I mean, this is ongoing, and eventually the aim would be to provide a block for the global fit, but I should conclude here. Thank you very much for your attention, and that's a big question.
Thank you very much. Questions? Yes.
Thank you very much for the nice talk. I have just a quick question. So let's say that the global fit is not able to remove all sources properly, but the background is below the noise floor of Lisa, so in principle you shouldn't be able to detect it. Would you detect a background and infer that it comes from cosmological or astrophysical origins incorrectly in that case? Or put another way, how good must the global fit be to enable this kind of cosmological inferences?
I mean, clearly, the better global fit does, the better it is. But even if it's not perfect, it depends on what you include in your analysis. I mean, in principle, you can, okay, in this, can I go back? Yes. I will get there eventually. So for all these results, we did include not only the noise and the stochastic background, but also the astrophysical components. So in principle, if you expect some extra contaminant to be there and you include it in your model, you're fine. It's just gonna, degrade the measurement, but it's not gonna give you a bias. If you don't include the extra component, you end up getting a bias. So it's more or less similar to what I was showing in this other plot. So if you just run an MCMC pipeline and you don't account for the fact that there can be other contaminants, you do get a bias.
No, but my question is the other way around. So if there is no background, okay, could you be misled into thinking there is one simply due to systematic subtraction errors?
Yes, but again, same thing is.
Yes.
Is the bias is pushing you up into seeing something which is not there? I mean, it's more or less like the thing you see here, no? Here, I'm not in the MCMC. I'm not including for the possibility of extra power being there, and my estimate is biased towards larger values because there is the extra power there. So you must be careful.
So this might be a little bit of a similar question, but I'm wondering for the astrophysical backgrounds, I'm assuming, for example, for the stellar mass black hole binaries, that you're just assuming that they're evolving purely through GR all the way through the Lisa band. Mm-hmm. And I'm wondering if there are, for example, important dynamical channels that are contributing to the LVK signals, then there will be frequency structure, for example, either if the binaries are forming at frequencies in the Lisa band or forming outside, but then having interactions that cause their semi-major axes to shrink, then is that a potential confounder, and how can you deal with that?
Very good question. Thanks. So I think is again the same thing. So let me go back to this plot. This guy. So here I've only included the minimal scenario, but in principle, if you include extra effects, what happens is that this shape changes. Clearly. So when you do the analysis, hopefully, you would want to go with something a little bit more general than just 2/3 and an amplitude. You should find a compromise between the two things in order to have something which is sufficiently good to model for extra things, but without being, if you're totally agnostic, in the end, you know, everything is correlated. So you must have some reasonably good understanding of what you expect from, you know, theory, and then you can build a model which is reasonable. I mean, this is what I would do. Yeah, exactly, exactly.
There is another question.
Yes. Thank you very much for the talk. It was very, very fantastic. I just had a question about the data that you've used to train your neural networks.
Mm-hmm.
And because, so you've tested your neural networks against MCMC.
Yes.
And I was wondering what kind of data you've trained it with. And also, if you've trained it with basically GR data, do you think that the same results would hold if you had non-GR effects? You would reconstruct as well your ground truth?
The answer you get is as good as the ingredients you put in your simulator. So for this thing, what we did is to generate frequency domain data, and we checked, you know, under the same assumptions on the two sides, we checked that you do get the same answer to the same question. If you modify the assumptions, basically going from GR, I mean, if you want to train a network so that it can also account for something beyond GR, you must include that in the simulator. If the simulator includes these effects, then you're able to model them properly. If you don't include them in the simulator, you're not going to model them properly. So, yeah, I hope this answered your question.
Okay, any last question? Don't see it. Okay, so thanks to speaker again.
Thank you.
And then we have an announcement by our local organizer.